A mathematician sat down and asked a question that would change civilization forever. Not can machines work faster than humans, not can machines store more data, but something far more unsettling. That mathematician was Alan Turing, and the question he asked ignited one of the greatest intellectual journeys in human history. This is not a story about robots. It's not science fiction. It's the story of how human beings tried to bottle intelligence itself, and what happened when they almost succeeded. This is the complete history of artificial intelligence. The idea of artificial minds didn't start in Silicon Valley. It started in myth. The ancient Greeks imagined Talos, a giant bronze automaton built by the god Hephaestus to patrol the shores of Crete. They dreamed of Pygmalion's statue, which came alive. These weren't just stories. They were a species projecting its deepest ambition onto the universe, the creation of artificial life. Fast forward to the 13th century. Ramon Lull builds a mechanical device, the Ars Magna, a logical machine intended to generate philosophical truths through combinations of concepts. It's primitive, but it's the first time someone tries to mechanize reasoning. Then Leibniz, then Boole. Slowly, painstakingly, humanity builds the foundations: formal logic, symbolic reasoning, binary mathematics, the intellectual scaffolding for a thinking machine. By the early 20th century, the pieces are almost in place. All they need is someone to build the engine. Alan Turing never built a brain. But in 1936, he did something arguably more important. He defined what computation itself means. His theoretical Turing machine, a conceptual device that could perform any calculation by reading and writing symbols on a tape, proved that logic could be mechanized. That reasoning itself had a structure. That structure could be encoded. Then came the war. Turing's code-breaking work at Bletchley Park wasn't just brilliant. It demonstrated that machines could perform tasks previously considered exclusively human: pattern recognition, inference, deduction under uncertainty. In 1950, he published Computing Machinery and Intelligence, the paper that launched a field. In it, he proposed the Turing test. If a machine could hold a conversation indistinguishable from a human, should we not say it is thinking? 6 years later, in the summer of 1956, a group of scientists gathered at Dartmouth College for a workshop that would formally name the discipline. John McCarthy, Marvin Minsky, Claude Shannon, Nathaniel Rochester. They called it artificial intelligence. The decade after Dartmouth was electric with optimism. Researchers believed, genuinely believed, that human-level AI was 10 years away, maybe 20. They built programs like the Logic Theorist, which proved mathematical theorems. Then Eliza, a chatbot so convincing that users formed emotional attachments to it, which terrified its creator, Joseph Weizenbaum. Then SHRDLU, which could manipulate virtual blocks in response to natural language commands. Governments poured in funding. The US Department of Defense, British research councils. The future, it seemed, was inevitable. Then, the Lighthill Report happened. In 1973, British mathematician Sir James Lighthill delivered a devastating review of AI research to the British government. His conclusion: AI had failed to produce any results of fundamental importance. The grand promises had not delivered. The problems were far harder than anyone admitted. Funding collapsed. Labs shuttered. The field entered what historians would later call the first AI winter. AI didn't stay dead. In the 1980s, it came back with a different pitch. Forget general intelligence. Let's build systems that capture the knowledge of human experts. Expert systems encoded the decision-making logic of doctors, lawyers, and engineers into rule-based programs. Mycin diagnosed bacterial infections. XCON configured computer hardware. Corporations paid millions to deploy them. By 1985, the AI industry was generating over $1 billion annually. Japan launched its fifth-generation computer project with billions in state backing. The West panicked and matched it, but expert systems had a fatal flaw. They were brittle. They could only do exactly what they were explicitly programmed to do. The real world is messy, ambiguous, and constantly changing. Rules couldn't capture that. While expert systems were failing, a small group of researchers was quietly pursuing a completely different approach. Not rules, not logic trees, something inspired by biology. The brain doesn't run on if-then statements. It learns. It adjusts. Billions of neurons fire and rewire based on experience. What if machines could do the same? In 1986, Geoffrey Hinton, David Rumelhart, and Ronald Williams published a landmark paper on backpropagation, an algorithm that let multi-layer neural networks actually learn from data by calculating and distributing error. It worked, in theory. But training neural networks required enormous amounts of data and computing power that simply didn't exist yet. The field remained a niche curiosity for over a decade. Then the internet happened. The web generated data at a scale no one had imagined, and GPU manufacturers, building chips for video games, accidentally created hardware perfectly suited to the matrix calculations neural networks required. In 2006, Hinton introduced deep belief networks. In 2009, Fei-Fei Li launched ImageNet, a dataset of over 14 million labeled images. In 2012, a deep convolutional neural network called AlexNet entered the ImageNet competition and didn't just win, it destroyed the competition. Its error rate was nearly half that of the next best system. The research community went silent for about 3 seconds, then erupted. The deep learning revolution had begun. Once deep learning proved itself, progress became exponential. 2016. DeepMind's AlphaGo defeats the world's best Go player, Lee Sedol, a game so complex that experts said it would take decades before AI could compete at the highest level. AlphaGo didn't just win. It invented moves that human players had never seen in the 3,000-year history of the game. 2017. A team at Google publishes Attention is All You Need, the paper introducing the transformer architecture. It's a dense research paper. Almost no one outside machine learning reads it. It quietly becomes the most important computer science paper of the decade. Transformers don't process sequences step by step. They look at everything at once, using a mechanism called self-attention that lets the model weigh the relevance of every word against every other word simultaneously. It's faster, it scales, and it unlocks something nobody predicted. 2018. Google releases BERT. OpenAI releases GPT, language models that understand context in ways previous systems never could. 2020, GPT-3 arrives, 175 billion parameters, the largest language model the world had ever seen. It writes essays, code, poetry, and legal briefs. It passes some professional licensing exams. Researchers start arguing about whether it's doing something more than pattern matching, or whether that question even makes sense. 2022. ChatGPT is released. Within 5 days, it reaches 1 million users. Within 2 months, 100 million. The fastest adopted consumer technology in history. Today, AI is no longer one field. It's many. Large language models from Anthropic, Google, Meta, and OpenAI generate text, code, and analysis at human expert level on a growing number of benchmarks. Multimodal models see, hear, and reason. Protein folding models like AlphaFold have unlocked biological mysteries that had resisted science for decades. AI systems are diagnosing cancers, designing chips, writing legislation drafts, and composing music. And the debate has shifted. It's no longer, can machines think? It's, what happens to society when they can? Questions about alignment, ensuring AI systems pursue goals humans actually want, have moved from philosophy seminars to government briefings. Questions about displacement, about access, about whose values get embedded in systems used by billions. These are not science fiction problems. They are present-tense problems. Researchers like Geoffrey Hinton, the man who helped create deep learning, have left their corporate positions to speak openly about risks. Governments have begun drafting regulatory frameworks. The EU passed the AI Act. The US issued executive orders. The UK hosted the first global AI safety summit. The field that was dismissed, defunded, and mocked through 2 brutal winters is now arguably the most consequential technology of our time. Alan Turing died in 1954, 2 years before the field he inspired was formally named. He never saw neural networks, never saw AlphaGo, never saw a language model write a sonnet or debug a codebase. But in 1950, he wrote something that feels almost prophetic now. We can only see a short distance ahead, but we can see plenty there that needs to be done. We've come an extraordinary distance since that blinking cursor on a wartime typewriter. And the next chapter is being written right now by researchers, by engineers, by policymakers, and increasingly by the systems themselves. Whether that next chapter is the best or most dangerous in human history may depend on how well we understand the one we just told.